Good morning, my dear 9G and 9B students. This is Miss Teresa. This time I'll be presenting to you a video guide for the air pressure worksheet. I've already uploaded this worksheet with the previous video lesson for barometer and manometer, but just in case you were not able to see it, I've uploaded it together with this video guide too. So what you need to do is open this video together with that worksheet so that you can follow along as I'm solving it. Or better yet, download the worksheet and solve along with me. If you've already solved it, then that's very good. Bear with me as I navigate through this presentation because I will be annotating it. My handwriting here will not be as legible because I'm doing it on my screen. So let's move along then. The success criteria for today is read and interpret pressure readings using a barometer and manometer. We'll be solving problems regarding these. Problem number 1. Problem number 1 states that figure 2.1 shows a container of gas connected to a manometer. The tube in the manometer has a constant cross-sectional area. The gas in the container exerts a pressure. Before you attack this problem, you need to open your eyes to the basics. So here they are. The density is given. You know its density because it's given in kilogram meter per cubic meter. The gravitational field strength is given, which is 10 Newton per kilogram. Sometimes they don't give this, but you should always know that G is equal to 10 Newton per kilogram. And the pressure of the atmosphere is 1.0 times 10 raised to 3 pascals. This time they gave it in Pascal. Sometimes they will give it in Newton per meter square. Sometimes they will give it in millimeter of mercury. Okay, so you have to be careful with your SI units. What else do you need to know about this problem? There is height over here, the height of the column of the mercury over here, which is easy to read. It's at 16 centimeters, but you have to change that into meters. Why do you need to change that into meters? Because your density is in kilogram per cubic meter. It's easier to change 16 meters to meters, so 0.16 meters. So those are your basics. Now you have all the things that you need to solve this problem. Okay, so the answer to this problem is 7.76 times 10 raised to 4 Pascal. That's the answer. But before I solve this, it will be beneficial for you to solve it first. So you can pause this video if you want, solve the problem by yourself and try to see if you'll get the same answer. Then you can self-check later. Now, I presume that you just did that. I'm going to solve it. So we know that P equals rho GH. Our rho is this one. So I'm going to change it to expanded notations. So this is 14,000, which is the same as 1.4 times 10 raised to 4. Okay, times G, which is 10 Newton per kilogram, times the height. Height is this one, and we mentioned earlier that this is 0.16 meters. Okay, 16 centimeters changed to meters, so 0.16. Okay, I'm gonna enter that in my calculator. 14,000 times 10 times 0.16 is 22,400 Pascal. So why is it not the same as this one? It says that this should be the final answer. So why did I get 22,400? What is that for? 22,400 is actually the pressure exerted by the column of the mercury on this side of the manometer. So that's 22,400 Pascal. Okay, so I'm just gonna clear that up. So if this is 22,400 Pascal exerted by the column of the mercury over here, and the air pressure is 1.0 times 10 raised to 5, Now, what is the pressure of the gas? In this case, air pressure is greater than the gas pressure. So if air pressure is greater than the gas pressure, what are we going to do? Are we going to minus air pressure minus the 22,400 Pascal, or are we going to get the difference, air pressure minus 22,400? So what will we do? Since the gas pressure is less, then we're going to minus. Okay, so this is 22,400 Pascal, and the atmospheric pressure is 1.0 times 10 raised to 5. 1.0 times 10 raised to 5 is the same as 100,000 minus 22,400 Pascal. So is equal to 77,600 Pascal, which is in standard notation is 7.76 times 10 raised to 1234 Pascal. So that's the final answer. Why is it 3 marks? Because the working until 22,400 Pascal should be shown. That's 1 mark. This is 1 mark, and the SI unit is also 1 mark, so 3 marks. So you should know that. Okay, so that's it. Next part of the problem. We're going to clear, and I'm going to the next. Okay, so I'll just move my screen over here. Okay, next part of the question. It's actually the same question, but another condition is added to it. Most IGCSE questions are like that. That is why if you do not like reading, then you would mostly lose all the details that you need to answer questions correctly. So I'm going to read. Okay. In figure 2.1, the mercury level on the left-hand side of the manometer is lower than on the right-hand side. The gas inside the container is heated. This causes the mercury levels on both sides to become the same. Determine the mercury level as shown on the ruler when this happens. So what is the question being asked here? So first, let's look closely at our manometer. So it says here that heat is added in this container. So if heat is added here, what will happen? This question is just asking you to use your common sense, not your mathematical skills. But of course, it's also testing your knowledge about the motion of molecules of a gas when they are heated. So the question is, what happens to the volume of a trapped gas when it is heated? Right, it expands. The misconception here, though, is that some students say that the molecules expand. No, the molecules do not expand, the volume does, because molecules here will vibrate faster when heat is supplied to the gas. Therefore, they need more space to do this. Hence, the space occupied by the gas expands. So, as the gas expands, it will push the column of mercury down this tube. As this right column goes down, okay, the left column will be going up correspondingly. One level down, let's clear that. One level down here will correspond to one level up over here. 2 levels down, of course, then 2 levels up here. And actually, it's asking you where will they meet? Where will they meet as it's going up and down? And they will meet at the answer here is actually 8 centimeters. Why? Because the right side starts at 16, then it will go to 15, left hand side will go to 1, 14, 2, 13, 3, and then so on, and then they will meet at 8 centimeters. So that's the answer for this question. So If you have any question about this problem, you can type your questions in the private message feature of Teams and I will answer them ASAP. Okay, so that's it. Problem number 2. Okay, problem number 2, it says figure 3.1 shows a glass tube dipped in mercury. A vacuum pump is connected to the top of the tube and switched on. The mercury rises up the tube and stops. This is how they make barometers actually. This will be connected like a straw to a vacuum tube, and this will be left as a vacuum also. Vacuum. Okay. Now in the video I already told you that there should be no air bubbles over here. Okay, so now the height of the tube, the mercury in the tube is 0.76 meters. The question, it says the 3 points in figure 3.1 are labeled P, Q, and R. State which 2 of these points are at atmospheric pressure. So easy. First answer straight away is R, right? R will be the answer, but it's asking you for 2. So what else? Is it P or is it Q? Okay. P and Q. So what do you think is the answer? So the answer here will be Q. Why? Because it is at the level, okay, of the point of the liquid where it's exposed to the atmosphere. So this is the point where it's exposed to the atmosphere, and that Q is also at the level where the mercury is exposed to the atmosphere. So the answer here should be Q and R, which is only 1 mark. So that's it. Next part of the question. Okay, I'll read it. Figure 3.1 shows a glass tube. Same thing. The density of the mercury is 13,600 kilogram per cubic meter, and gravitational field strength is again given, and the column of the mercury is 0.76 meters. You are going to calculate for pressure. So the answer to this, wait please. The answer to this is 1.0336 times 10 raised to 5 Newton per meter squared, or Pascal. So pause the video, work the problem out, and see if you get the same answer. Okay. Now I assume that you just did that. I will solve it now. So we always know that P is equal to rho GH, right? So the density rho is 13,600 kilogram per cubic meter. So 13,600 times G is 10 times height is 0.76. So calculating that, 13,600 times 10 times 0.76 is 103,360 Newton per meter squared, but you have to change it to standard notation. So 1.0336 times 10 raised to 1, 2, 3, 4, 5 raised to 5 Newton per meter squared. So that's the answer. If you got the same answer, then you give yourself a high five and a good job. Okay, so that's it. If you have any question about this, you give me a private message in Microsoft Teams. Okay, let's go to the next part of the question. So in here it says state and explain. A vacuum pump is connected to the top, same thing, And it says state and explain what happens if the mercury in the apparatus shown in figure 3.1 is replaced with water. What do you think will happen? This question will test your knowledge of density of different liquids. So my question is, which is denser, mercury or water? Right, it's mercury. So if we have, let's say, in a tube, which is, let's say, 10 cubic centimeter of water, and another tube, we're going to have 10 cubic centimeter of mercury. Okay, so 10 centimeter cube of water in a cylinder, and another similar cylinder which also containing 10 cubic centimeter of water. So the other one is water, the other one is mercury. Okay, in which cylinder will the liquid rise higher? So the answer will be the cylinder with water. Why? Since mercury is denser, okay, it indicates that the particles are more compact. So in here, okay, so if this is Hg, okay, 10 cubic centimeter of Hg, and here same 10 cubic centimeter of water. Okay, the column of the water, H2O, will rise higher. Although they have the same volume, the column of water will rise higher than the column of mercury, because mercury is denser. Consequently, the column of mercury would not rise as high as the column of water at the same volume. Okay, so in here, your answer here should be the column of the tube will rise higher. Why? Because it's less dense. Water is less dense. Okay, so moving on. Let's go on to the next page. Wait, please bear with me. Next page. Next question. Okay, problem number 3. I'm going to read it. Okay, a small crack appears in an oil tank and a stream of oil is pushed out through the crack. The oil hits the floor at P. Okay, in here. Okay, this is P, where a puddle of oil starts to form. Okay, the gravitational field strength G is equal to 10 Newton per kilogram. The density of the oil is 940 kilogram per cubic meter, and the crack is 3.3 meter below the surface of the oil. Now you're going to solve for the pressure. So again, this question, you should automatically already know that this is a P is equal to rho GH question. The answer to this question is 3.102 times 10 raised to 4 Pascal. Okay, again, pause the video and work it out, and then we're going to solve it. Then you compare your answer with me. Okay, so let's solve it together. P is equal to rho GH. So P is, and the density is 940 kilogram per cubic meter, times G is 10, and times H is 3.3 meters. Do we need to change it into another SI unit? No need, because everything are the same. Okay, they are all the same. So 940, wait please, I'm gonna calculate it. Okay, calculator. 940 times 10 times 3.3 is 31,020. Okay, 31,020 Pascal. Okay, So 31,020. What answer did I say earlier? The answer I said is 3.102 times 10 raised to 4 Pascal. Is it the same? 2, 3, 4. Yes, it's the same. Now, if they ask you to answer it with two significant figures, then you just answer 3.1 times 10 raised to 4 Pascal. And if they ask you to use Newton per meter squared, you can also use that, which is equal to Pascal. They don't ask you to actually convert Newton per meter squared to Newton per cm squared. That will be an AS level question, and this is just IGCSE level. Okay, so that's it for that question. Now let's go to the next. Same question, but another is given. Okay, I will read. The density of the oil is 940 kilogram per cubic meter, and the crack is 3.3 meter below the surface of the oil. Explain why the atmospheric pressure does not affect the rate at which the oil is pushed out of the crack. Okay, so what is this question asking? Okay, this question is asking you whether the atmospheric pressure, here is the atmospheric pressure, is the atmospheric pressure affecting the way that the oil is pushed out of this crack? Will it affect it? Okay, so some questions will ask you whether atmospheric pressure affects the oil in this crack. In this question, it's simpler than that. We already know that the air pressure does not affect the oil being pushed out of the crack. So take a guess. No, not just a guess, an educated guess about this. Apply your knowledge of forces in this question. Pause the video before I go on explaining about it. Okay, so here's the explanation. Atmospheric pressure acts at both ends of the crack. Okay, so why atmospheric pressure acts over here as well as here at both ends of the crack. Therefore, the force exerted by the atmospheric pressure on both sides negate each other. Negate. What does negate mean? In other words, they cancel each other out. So, if they cancel each other out, therefore, it doesn't affect the oil being pushed out of the crack. Plus, our formula is P is equal to rho GH. Is there any atmospheric pressure present in this formula? No, there's none. So, explain why the atmospheric pressure does not affect the rate at which the oil is pushed out of the crack. The answer is atmospheric pressure acts at both ends of the crack, therefore they will cancel each other out. That's it. Okay, next. This question is the same, but additional extended question. As time passes, the point where the oil hits the ground, the floor, moves away from P, okay, towards the tank. It might move towards here. Okay, so it might fall this way, not that far anymore. Okay, explain why this happens. Why do you think this happens? This is easy. Since the level of the liquid decreases, then consequently the pressure of the crack also lessens or decreases. No other technical explanations about it. Okay, so if you got all the answers correctly for this problem, give yourself a pat on the back. Very good. Good job. Okay, let's go to the next problem. Problem number 4. This is actually just a simple barometer. So, figure 4.1 shows a mercury barometer. The tube containing the mercury is vertical. Okay, the height h indicates the value of the atmospheric pressure. State what is contained in the space labeled S. This one. What is this? What is in this space? This is very easy. It's just vacuum, which is already discussed again and again in class as well as in the video. Now, the second question is again P is equal to rho GH question, but we're going to solve for the H instead of P. Okay, so the second part of the question, the answer is 0.75 meters. I'm not going to solve it anymore. I think you already know how to manipulate the formula to get H. So okay, I'll just show you how to use the formula to get H. P is equal to rho GH. We need H, so H is equal to P divided by rho G. Okay, this formula is what you're going to need to solve for 0.75 meters. I'm not gonna solve it anymore. That's the final answer here. If you didn't get it, then you can ask me a question in the private message part of the Microsoft Teams. Okay, so let's go to the next. Okay, same question but different situation, different conditions. Okay, the tube containing the mercury is now tilted, so it makes an angle of 10 degrees with the vertical. After tilting, there continues to be a space above the mercury in the tube. State and explain whether the vertical height of the mercury in this tube is smaller, the same, or greater than the value calculated in A2. Okay, so what's your educated guess in this? Do you think the level of H will change? So it's like this is your barometer. It will just be tilted this way. So it will be tilted this way. Okay, you still have your at 10 degrees. So will this H change? Will the H change? Will the height change? Will it change if you tilt it this way? Will it change? Okay, so in here the correct answer is it will be the same. Why? The H will be the same. Why is it the same? Because tilting the glass does not affect the height of the mercury column. Okay, nor does if you are going to use a bigger column of mercury over here. Will it change the height? No, it will still be the same because the shape does not matter, the angle does not matter, because P is equal to rho GH. Is there angle in here? Does angle affect it? The pressure? No, it does not. Does the shape affect it? Is there a form in our formula? Is there something about shape? No, it doesn't. So it will still be the same. So tilting angle does not change the height of the mercury column. The shape does not change the height of the mercury column. Okay, the pressure are the same at each of the points at here, this one, because the pressure does not depend on the container angle, it does not depend on width, or it does not depend on shape. Okay, so that's it. Next question. So same question, different condition. Another mercury barometer in the same room at the same time shows a lower value of H than the barometer. Okay, so suggest and explain a reason for the lower value. Just tells you that there's a similar barometer, it's in the same room, and of course if it's in the same room, the air pressure will be the same, but in this case the barometer has a lower H, so lower height. What do you think happened? Why does it have a lower height of column of mercury inside the barometer? They are in the same condition, they are the same size of mercury barometer, they have the same amount of mercury present. So what do you think is wrong with the second barometer? Okay, so if you have watched the video about barometers and manometers, you should know by now that this part of the barometer should be a vacuum. Okay, a vacuum. So if there are air bubbles present here, okay, your barometer reading will be affected because the air will exert a force, the air bubbles will exert a force opposing the air pressure. Okay, so that will be the reason why there will be a lower value of H. Okay, so that's the answer. So if you answered all these questions correctly, congratulate yourself. You are now a barometer expert. Okay, problem number 5. We're going to problem number 5 now. Okay, problem number 5. This is the last problem. Okay, figure 4.1 shows a manometer containing mercury being used to monitor the pressure of a gas supply. Okay. What is the value of the excess pressure of the gas supply measured in millimeter of mercury? So this question is just asking you the pressure difference between the two tubes in here. So let's go and look at it closely. Yeah, magnify like this. Okay, so in this case, the right hand side shows that it's at the level of 160 millimeter of mercury, whereas the left hand is showing you that it's at 70 millimeter of mercury. Now if you're going to get the difference between that, it's just of course 160 minus 160 minus 70, which is equal to 90 millimeter of mercury. Okay, bear in mind, without the unit, you won't get 1 mark. This is only for 1 mark, and if you didn't write the unit, you won't get it. Okay, so SI unit is very important. Next part. Okay, same question, different conditions. Okay, so the atmospheric pressure is 750 millimeter of mercury. Calculate the actual pressure of the gas supply. In this case, I want you all to send me an answer in the private message. I want to know if you all listened up to this point of this boring video guide. Tell me how you got the answer also. That way I can check if you're present today in our online class. So this one I will not answer. You're going to answer. You're going to send me your answer in the private message. Okay, so let's move on. Last, same question, different conditions. Okay, the gas pressure now decreases by 20 millimeter of mercury. On figure 4.1, mark the new positions of the two mercury levels. You're going to draw here, somewhere here also, where is the new position of the mercury levels if the gas supply decreases by 20 millimeter of mercury. So let's look at it closely again in here. Okay, so the right answer to this, I'm gonna give it to you immediately. Okay, the answer at the right hand tube, it should be at 150 millimeter of mercury, and on the left hand tube it should be at 80 millimeter of mercury. Okay, I'm sure most of you will answer like it should be 140 millimeter of mercury at the right hand tube and 90 millimeter of mercury at the left hand tube, because it says here that the gas pressure decreases by 20, so it should go up, this side should go up by 20 and this side should go up by 20. Most of the 9B and 9B1 boys last year also answered that way, and we had a period long debate about it. But as you can see in here, okay, one level down here means one level up here, and if you're going to add that together, it's already 20 millimeter of mercury. This is a U-shaped manometer. The fluid measures both ways, not just one way. So it should be at the level here, you're going to draw at 150 millimeter of mercury, and here at 80 millimeter of mercury. Okay, so boys and girls, that's it. That's all for now. I hope you had I hope I had explained all the questions well. If you still have doubts, feel free to message me in the private chat. I will try to answer the best I can. So today, what did we learn today? Okay. Today we learned what? Okay, wait, please. So, okay.